lecture. Did y'all see it? All right, I think included in there was radar, right? And there was, I'm trying to think. I believe there was also a discussion about beamforming using antenna arrays. Wasn't there? Didn't have a ray factor in there or not? All right, we're going to cover that. Here's what I want to do. I'm sorry if you did. It's okay. You see, I gave you enough. So if you had radar down there, now you have all the things that we'll be using electromagnetic antennas for, really. There would be radar and communication. Follow me on this, class? So now I'm just going to cover the one thing that helps a single antenna become much more directive or give it much more focusing power, and that's using an array factor, right? Using constructive and destructive interference by adding more antennas. What I want to do is give you a page number in the book before I get started on this. If you haven't got your test back and you want it, after class, walk with me to my office and I'll give it to you, okay? I thought I haven't, I guess I didn't have it here. So it did cover monopoles, right, in the lecture? Okay, monopoles. It did, I believe, the frequency transmission and radar, right? I'm trying to think entirely of everything in there. What's that? Yeah, the imaging is real important. That's where you get the monopole. But y'all, did you have questions about that? I'll start there, right? Anything at all? Or about the actual antennas equivalent model? Go ahead, Tyler.
If you're given a gain, and I was looking at the book, it said it's like unitless, but it can be denoted with dB.
Gain is got two factors. It's either a linear number, like 1, 2, 3, 4, 5, or it's in dB, and I'll give you the relationship in 1 second, okay? Looking for one thing in here. Stu's book is not laid out the way I would like, but it's a good book. I'll put it to you this way: it doesn't get too deep into the theory, so you get overwhelmed. So if you look, actually, this is on page 473. Now, about gain, I just want to put everybody on the same footing here to make it clear about it. Gain is a measure of the focusing power. We know the mathematical definition for gain, or directivity, right? Now, I'm going to put that up here. I'm going to draw something. So I know directivity here is equal technically to 4 pi. Oh, you don't have to write this down. Over the integral over the surface of the normalized power density of theta phi times the sine of theta, d theta d phi. And of course, theta would technically go from 0 to pi, and phi would go from 0 to 2 pi. Now, this is a standard definition we talked about, right? You don't have to write that, just for everybody's, to jog your memory. Gain itself is the efficiency times directivity. Usually the efficiency is about 100% or 1. Okay? Almost, I mean, if it isn't, you got a problem. If it's like 30%, I mean, you basically got one of the worst antennas in the world. Now, if you're looking at how well something radiates that shouldn't radiate, then you'll need to calculate the efficiency. More on that later. With me? All right. Now, when we talk about dB, this is the real thing. Any number in dB, this is going to be dB. And put down if it is a power-related term. Gain is related to power. It has to do with the gain times the isotropic power density is the power density that's increased by that focusing power of gain. Okay? So if that's the case, we talk about dB, it's equal to 10 times the log of whatever the number is, linear. Now, if it's gain dB, this would be gain linear. Let me just give you a singular example. If I had a gain of 100, that's a linear gain. Well, 10 times the log, this is a base 10 log, by the way, of 100. Well, the log of 10 squared is 2, right? Times 10 would be 20, and therefore this would be 20 dB of gain. if I had a gain of 10,000, what would it be in dB? Just basically doing the math. 10,000 is 10 to the fourth. Agreed, class? What's the log base 10 of 10 to the fourth? Just pull 4 out front, right? Isn't that right? Log of n, 10 to the n, log base 10 of 10 to the n is n. Just so everybody knows, log base 10 of any 10 to the nth number is just n. All right? I think we all know that, but I put that on there just in case. Got it, everyone? That's all it amounts to. So what would the log of 10 to the fourth, of 10,000 be? And dB? Sorry, what would the dB gain be?
40?
Sure, 40 dB. And you can see the progression, right? I'm just making sure we're all... Now, I got to tell you one other thing about gain. If it's volts or current, then it's 20. So if you talk about a voltage or current, then we talk about dB of whatever is equal to 20 times the log base 10 of whatever. I think we all know that, but I'm just making sure. Some of you may be bored. Hang with me, all right? Now, that's not the end of the story. Almost always in the real world, we just don't take a look at log of the current. What we do is normalize. Do you have a question? Do you need clarification? No. Okay. You were looking hard there. I didn't know if you couldn't read my writing, because her notes are salvation in this class. If you can't read my scribbles, go to her notes. Now, anyway, so what we usually do is we normalize to something that's common, that we know. So a lot of times what we'll do is talk about dB microvolts. This is very common. It would dB microvolts. And that's equal to 20 times the log, and that's a log base 10. Please note in MATLAB, if you type log of 10, you don't get 1. All right? Log of 10 is the natural log. You have to put log 10. Do you all know that? Please don't forget that. It'll save you some pain. MATLAB's something, I'm going to just throw out this. MATLAB, Octave, Python, pick your poison in a sense. You're going to use these things if you got in the real world, almost guaranteed. They're called prototyping languages because they're higher order languages. They're very easy to do complicated processing things in, mathematical processing, matrix inversion. Then once you get the code down to the way you like working it, they do a port to C, they'll do a C conversion. All right, they have these compilers that'll do it, and they'll take the compiled code and use it on like a microcontroller or microprocessor. Y'all know this class? So don't hate MATLAB, don't hate Octave, don't hate Python. There's a learning curve, but believe me, you'll be thankful because there's so... Matter of fact, I can tell you this, if you know embedded programming now, that's using C programming to do microcontrollers, and you're an electrical engineer, you can write your ticket about anywhere from what I've been told. My wife works at a place that does this very thing. For what they're doing is they're retrofitting old aircraft radars and things like this, other things, navigational systems, with modern digital technologies for display. So it's legacy, and microcontrollers are used for it. She's got job offers everywhere. They would love her to go to California, some other places. So just remember this, all right? If you get to take like the PLC class here? Is there one? There's courses that deal with embedded systems and microcontrollers. Check them out and learn from that. You'll never regret it, and you'll thank me 10 years from now. All right, anyway, so dB microvolts is the actual voltage over 10 to the minus 6. And can anybody guess what dB microamps is? Take a guess. 20 points.
20 log 10?
It's 20 log what? Anybody? Log base 10 of not VI, right? Over 10 to the minus 6. I didn't put that down there, but that V and I have to be a magnitude. Don't put a really imaginary number there. You put an imaginary number in the log. I promise you people do this on tests because they sort of get panicked. Well, that's my calculator. It says it.
We did 20 points.
That's debatable. All right, now there's one more. These two are common. There's one more. And that is dBm for power. And this is a power term. So dBm is actually equal to 10 times the log, not 20, base 10 of the actual power over 10 to the minus third. And the reason we use dB so often is because many times the dynamic range means how many orders of magnitude things change. In radar processing or telecommunications, you might get 12, 15 orders of magnitude change. Well, you know, on your calculator, if you look at 1, you don't know what that is. Even 1 times 10 to the minus 21st or something like this, you're scratching your head. What's that? What can I do to make that somewhat analogous to give me a representative idea? Well, noise threshold for most processing, not all. It depends on a lot of things. But generally speaking, if you get less than, I'd say, minus 100 dBm, you can forget about that being anything that you have to worry about. Now, there are exceptions for deep space astronomy and stuff like this. To get things at about a dB of minus 60 dBm is way, way down there. Your phone, if you know how to get to it, and most of these modern phones do, my old one did too, I had an old flip phone, will give the power that you're actually receiving in dBm, and it would be about minus 80 dBm if you take a look. Does anybody know how to do this on your phone?
Yeah.
You can, I don't know what it is down here, to be frank about it. I haven't done this down here. But it's about minus 60 to minus 80 dBm. If somebody does it, let me know, just for kicks. So just to give you an idea. And that gives you a good reference number. Like, you know, well, that's about, somebody says, I got a signal strength here, minus 200 dBm. Yeah, so what? So that doesn't mean a thing to me. I can't do anything with that. All right, now, back to the lecture stuff. I hope I didn't take too much time. Now, questions about the actual homework. Tyler, your question may have helped everybody get back in step after spring break, even though we weren't supposed to have a spring break. So you're recording this. Oh, that's all right. I think I'm allowed to say that. I haven't really gotten in trouble for much stuff I've been recorded saying. Got a lot of comments on certain things long ago. Never got in trouble. Any questions about the homework or about anything we covered? You all good with imaging? Just real quick, if we have a conductor surface, right, and we talk about imaging, we'll get to this stuff in a second. When we talk about imaging, what happens? Well, if we have a positive charge here, a distance h below, we come up a distance h above and we put a negative charge, right? Call this plus q and minus q. You agree? Whatever the charge value is, it images the opposite at the same height, right? The reason we do imaging is so we don't have to solve a differential equation. For instance, if it was electrostatics, you'd have to solve del squared the potential V is minus to rho over epsilon. Here, rho would be a delta function. That's a differential equation. That's a pain in the butt. You have to match boundary conditions. There's zero potential here if it's a good conductor. With me? If you saw the lecture, this should make perfect sense. With me? So this way, the only thing you have to do is you want the voltage out here or electric field. You simply look at these two charge sources at distance R1 and R2. Find the voltage caused by this as if the ground plane is removed at that point. Find the voltage caused by this charge as if the ground plane is removed and add it together. Did they do method of imaging and electrostatics for you or not? Did anybody have a need for electrostatics? Okay. I don't know. Well, I don't remember if I did it or not, to tell you the truth. Usually I do. So that's imaging of charge, right? Now with current, Is everybody okay with this? Let me see your hands if you are. Okay? All right. Now this is going to be current. This is imaging charge. All right. Start. This just means anytime you see this, that's considered ground. It's a perfect conductor. It's a piece of copper. Think of it that way. Thick piece of copper. Now, anytime you have something like this in the image currents, here's how we do it. If I have a current here, in this direction, the thing has a length L. We don't image the actual current here. What we do is say, and we could, but there's a lot more to this. I mean, we are going to eventually. Let me just show you. If you have any current, y'all agree that negative charge would be here and positive charge would be here, right? Just look at the direction. It would accumulate positive. Do you all agree with that? Just think about it rationally, right? Well, if that's negative charge and this is at a height h, then I'm going to move down a height h and I'm going to put positive charge. And I'm going to move down a height h and I'm going to put negative charge, right? Agreed? But I'm not done. What does that really look like in terms of the current down here? Well, positive was going to the positive terminal. It means positive is going to the negative, or to this terminal here, the image, the negative image, or the currents that are parallel image in opposite directions. Y'all got that? How many remember that from a lecture? Now, if you do the same reasoning, where I have perfect conductor, but now I have a current going in this direction, H, current has length L, and this is the way you always approach this thing. Always think of charging. So this would have a negative charge because current's leaving that area. Do you agree with that? A negative sense to it. Agreed, everyone? And the top part would have a positive charge associated. So if I come down a distance h, I would simply put a plus charge. And then that plus charge would image negative here. And the distance here would be L. Y'all agree with that? This is the rationale. I hope I explained it that way in the lecture. Now, you simply just show what an actual current would cause that, and the current would be in this direction. The moral of the story is currents in the same direction, vertical currents always image in the same direction. If it's going up, its image is up. If it's going down, its image is down. With me? Currents that are parallel image in opposite directions. Now we extend the rationale. Well, what if they're both? Well, you just do the component thing. If this is a ground plane, I don't remember if I covered it in that lecture, and this is a current I, this is a height h. Call that h1, this is h2. All right, that images, if that's this would be a negative charge, right? And this would be a positive charge. You agree with this, everyone? Can you see it back there? Okay. All right, negative images positive, right? I think this is in his book, I don't remember. All right, the other one's positive, it images negative, right? And that means the current will image like this. Same exact shape, magnitude, everything. The image current will have the horizontal components in opposite direction, the vertical in the same. That's it. Got me? All right, now, Last thing, and I gave you this, what happens to things like gain and all that stuff? Radiation resistance. I'll give you maybe a 3-minute nutshell what happens. Anybody go down to the beach? You went down Pensacola or where?
Desperate.
Was it crowded?
No, there's no one there.
Good. If I could have, I would have gone down to Fort Warren. All right, finally, I'm trying to wrap up everything before I get into the array factor. Finally, when we talk about real-world antennas, what's the effect? They're called monopoles. And if you watch the lecture, I talked about monopoles. So what's a monopole? It's half the length of the dipole you're talking about. That's all it is. So if we talk about a short dipole, if this is going to be length L, well, really, there's an image down here of length L as already. Do y'all follow? Everybody good on that? Now, if you want the electric field, I'm going to go from the center of this image. If I want the electric field out here at some range R, let's assume R is much greater than lambda. So it's just way out. It's far field. We're only worried about far field. Well, if you want E, that's a short, I'm going to say short dipole right here. Short dipole. The reason I'm saying short dipole is people could think, well, that's true for every monopole. So I'm trying to be careful, right? It's not. It's a short dipole. What's the reason? What's the criteria of short dipole?
Lambda's,
What's the length of the, what's it always? The length of the antenna is lambda over
20.
10. 10, it would be 20 for just the top part. She's right there, but it's, 10. It would be 5 for the, if this total length is less, this total length, the image included, is less than lambda, all right, over 10, it's short. All right, if it's greater than that, not so much. Then you have to, and once you hit close to about a quarter wavelength, then you got to go to that formula for arbitrarily long straight wire antennas. But the E field for a short dipole, in general, is J eta beta. This is Dr. Wentworth's way of doing it. Times I naught times e to the minus j beta r, right? And then it's going to be times the sine of theta over 4 pi r. And then it's times L. I wanted to put L out here. Times L in the A theta direction. L is the length. Well, here's a mistake. They'll use this length. It's not that length. That length is double that. Maybe I should use capital out there. Y'all with me? So this length here, L, that I'm showing you, would actually be the 2 small l that I'm showing you. That'd be the electric field. You with me on this? Now, something else about this. Is there an electric field out here below the surface class? No, right? There is none. So one logical way of thinking about this, well, if I'm radiating with an actual dipole a certain amount of power, then with a monopole that would be the adjusted length, like if this was a quarter wavelength, it would be a half wavelength dipole, right? In other words, if this was a quarter wavelength, this image would be a quarter, it would actually be a half wavelength dipole, wouldn't it, class? Right? Well, the power, the electric field from a half-wave dipole will be the same for a monopole of a quarter wavelength. But the power radiated is only radiated over the upper half. It's exactly 1/2 of the total power radiated by a dipole of equivalent length. Does that make sense to everybody? I can't radiate in under the, you might say, under the conductor. Follow me? Now, the reason I'm saying that is, what happens is, if I tell you that I'm radiating a total power of so many watts or something like this, there's a couple things that come to mind. Well, what's the gain? That should be your first question. What's the gain? And the way you figure that out is, because all the power is radiated only over half the space, the gain of the antenna, as if it was either a half-wave dipole, or quarter-wave monopole, half-wave dipole, or of a short dipole adjusted for that length, you take that gain and multiply by 2. Because the power is now just in the upper half plane. Are you with me on this, class? Or directivity. Now, I think I said that in the lecture, didn't I? Okay, good. What that means is this. Let's do an example. For a short dipole, right, the gain, well, let me put directivity down. Directivity is 1.5 times the sine squared, times sine squared theta, and that's for a short dipole. And again, theta is always measured from the z-axis of the antenna. You with me, class? Now, if you have a short monopole, then the directivity is going to be 3 times the sine squared of theta. With me? Did I cover that in that lecture? Okay, good. I think I did. I'm just making sure. His head's bobbing. Thank you. All right? Now, something else. There's one other thing that changes. Well, if you have a half-wave dipole, right? Or a quarter-wave, or a short dipole for that matter, you know you got a certain radiation resistance, right? Correct, class? The radiation resistance will be half that. And I'm trying to figure out, because for a given current, you're radiating half as much power. Does that make sense? The power is only going up in a half plane. What I'm trying to do is show you, let me show you what these things are in the book, because I hope I'm saying things that aren't confusing here. All right, if you look on page 466, the very last column is quarter wave monopole. Right next to that is half wave dipole. Anybody looking in your book? If you just write this down, if you have a book, you can look there. If not, don't worry. What I want you to take note of is the resistance at the bottom. For a half wave dipole, an ideal half, it's 73.2 ohms, isn't it? What is it for a quarter wave monopole?
36.6.
Exactly half. All right, it's half of that. You with me? So the radiation resistance will come down, but it would be a quarter wave monopole, not a half wave. Right? So the length of that monopole is really just half of a full dipole. If you also look at the gain for a second, for a half wave dipole, the peak gain, or directivity, I should say, is 1.64. Do you see that? How many have books here, by the way? Some of you don't. I want to make sure everybody's got this right. You see there, 1.64? There's a directivity doubles. That's right. There it goes from this way. 1.64, 3.2. It doubles. And radiation resistance goes down by that. I'll tell you one thing, you're good. If you can add that to the notes, it would be great. So that's how you get it for any antenna. Now the thing is, he doesn't put the shortwave dipole down, and I want to just make mention of this. Here's my short dipole, right? I put the image in here, and I made note that that L would actually be 2L, all right? Got that? If you would just want the electric field. Everybody knows how to get the H, right? You just take that electric field, if it was free space, divided by 8 and up, you got the H field, right? The power density, you could take what? You could take that electric field's magnitude, square it, right? And divide by 2 magnitude of 8 and up, right? Now you have the power density. Technically, you got everything you want just from that. You with me? And you don't have to fuss around with thinking, oh my goodness, the gain goes up by this much. And I see this on tests, is what I'm telling you. What you can do is use this golden rule right here. So then, Dr. Baginski, will you give us that one? Yes. For a short diet. Just so you know, I'm trying to be over the top, straightforward. Now, if you want to use directivity, if you want to use radiation resistance, go ahead, knock yourself out, but this is easy. Short dipoles, they cause people too much thinking. Well, do I use this L or do I use this L in that equation? It's always the image length if you're using a full length antenna's electric field. And I can keep adjusting that to do anything. I don't know if he has that for a short monopole in there. Hertzian, we call it Hertzian. No, he doesn't have a Hertzian monopole. But that's the problem. People mess that one up. Okay? Got me on that? All right. Now, next thing I'm going to do is arrays. Does anybody have any questions about anything else? Yeah.
Just making sure I understand what you're saying. You're saying you just deal with that equation, the E, instead of trying to
Well,
change the
look,
directivity?
if you're, let me just answer you with a direct answer. All right? If you would, whatever this length L is, if you double that, you get that L that goes in that equation. That's an equation that kind of, I know by heart. Maybe you don't, but I use it so often. I know that by heart. Now, once I have the E field, that's all I need for anything other. Right? If I got the E field, I got the H field. If I got the E field, I got the power density, right? If I want the gain, I can take the power density and normalize it. And then I can integrate it over the surface, but the surface is only 1/2 the actual surface of a full sphere, right? Because there's no radiation below the horizontal plane. And that means, effectively, that the directivity will be twice that. It'll actually be 3 times the sine squared of thing. You can write that down. All right? Yeah. And now, so people say, well, why don't I just use that directivity to get the power density? You could, but how much power is radiated? Depends what you know in the problem. If you know the actual current, just get the electric field. If you know the total power, then use the gain. Because that times that gain, or directivity, gives you the power density. Follow me? So, it has to do with that. Okay. I mean, that's like too simple. You take the isotropic power density, and then you would multiply by 3. Any other questions? I'll give you some homework to straighten that out. Everybody okay? Now, what I'd like to do is arrays, and I want to make sure, hopefully everybody's up to speed. I mean, this brought back everybody to what we're doing. And now I want to talk about arrays. Now, arrays are so powerful, but some people just get, I shouldn't say so. I would guess that there are those that probably feel a bit overwhelmed by some of these mathematics. It's not to be overwhelmed. We're engineers, we use complex mathematics all the time in advanced math. We use it when we need it. So, when I start, this is the way I do my lecture. One person's a little different. I start and I assume isotropic radiators. That means I'm going to take sources that have no gain. They radiate power or electric field the same in every direction. Are you with me? Now what I'm going to do, I'm making this as general as I can, as simple as I can. I'm going to go ahead and I'm going to say I have my first antenna here. I'll label that 1, or maybe 0. Here's my second antenna. Sorry, call this 1. Call this 2. Here's my nth antenna. These are all little antennas. I'm going to keep the separation distance between these antennas constant. And I'm going to make them D separation. So there always is going to be a D separation between them. With me? For isotropic radiators, there's D separation. I'm going to do one other thing. I'm going to say that this current here, on the first one, is I naught. This current here is I naught, but it can have a possible phase change of alpha. This is called a progressive phase change. On the second one, it'll be I naught, same magnitude, but then it'll e to the j2 alpha. Now, these are just phase changes. It could be something like 5 degrees. It would be I naught at 0 degrees, I naught at 5 degrees, I naught at 10 degrees. Follow me? Then we keep going out here. It would be simply I naught, the current would be e to the j n alpha. So I know the current and the spacing. I'm assuming they're isotropic radiators. And I'm assuming if I go out a distance r, and by the way, I didn't put this down there, we'll call this length equal to nd, it would be the number of elements times the spacing, and say that that is going to be equal to much, much less than r. In other words, we're in the far field for this. Everybody okay with that? So if we're in the far field, I want you to just watch. We're in the far field, it means a whole long ways away. Then there's some target out here, like 5 miles away, and that's at a point P. Can you imagine that here? It's like I'm from here to Weagle FM's antenna on top of Haley. And now I move a little bit, so I move this far away. Does this vector out that way look like it bent any? How about if I move this far? Until I start moving of the order of a tenth of r, it looks the same. There's no effective angular bend. All right, now this one next to it, call this r naught. Call this r1. Well, r1 is going to be parallel to r naught for all intents and purposes. With me? You can think about looking at a star if it helps. Just move. The star is always at the same azimuth and elevation. That's where our point is at a star. But what is the difference in this? There's a very slight difference in distance, isn't there? It's this distance right here. Can everybody see this? So this distance here, d, or I won't call it d. Let me call it L, right there. This length L would actually be d times the cosine of theta. And I'm going to just show you what theta is. Theta is going to be the angle that radius vector r makes with the axis of the antenna. All with me? I'm doing it this way for a reason. It'll make it a lot easier. And also be consistent with Wentworth's order. Now take a look at this. If phi comes down here and I'm looking this direction, well, the cosine would be cosine of 0 or 1, and the distance difference would be d. You agree with that? Think about it. What if I'm looking straight up? Well, if I'm looking straight up, what's the difference distance in this or this ray? Anything? Nothing, right? Just think of if you have two vectors like this. Well, if your point's a long ways away, and now if they're like this, there is no difference in distance, is there? Can you see it okay back there? With me on this? So that length difference is d cosine theta. Now, bear with me on this one. You can open that back door. It's getting warm in here. Keep everybody awake. Whenever I see yawns, I feel a little tired. I know it's time to get some air. All right, stay with me on this. Now, what I'm going to do here, out here, is get this value of E. That's what my job is. So I'm going to say up here that E, from this first one, this antenna right here, that's the 0th antenna. I'm just going to say it's going to be because I can do what I want, it's going to be K times the current I naught all right, over R. This is an isotropic radiator, we're making this as easy as possible. And it would be e to the minus j beta r. Don't even worry about a vector direction. If you want to put one in there, put anything. It doesn't matter. You all agree that would be the that if I say it's an isotropic radiator, it can't have an angular variation. You with me with the electric field? All right. If it did, then it wouldn't have an isotropic. If I put a sine theta there, now that doesn't have the same electric field for all distances r. You with me? And I just chose it. Somebody's going to say, well, what's K? It doesn't matter. It won't matter. That's an isotropic radiator. Electric field from an isotropic radiator. Now, what about the second one? This would be R0, actually. The second one would be plus K I naught over, now it would be R1, and then it would be e to the minus j beta, but not R naught, it would be R1. But what is R1? Isn't it just R naught minus d cosine, or I should put d here. Yeah, that is right. This distance L is just d cosine theta. You with me? Sorry. So it's going to be this times, and it would be R naught minus d cosine of phi, actually, not theta. Let me do one more, and you'll see the progression. What about the third one? Same magnitude, right? And I forgot one thing, and I'll put it in. Over R2, and it's going to be e to the minus j beta here, and then it's going to be R naught, but it's going to be minus 2d cosine of phi. Let me tell you why. For this one, where this is going to be R2, you can see the difference in path length is going to be 2 times the actual difference in path lengths for the first one. You all see that? All right. Now, something I forgot. Did anybody catch me with what I forgot to put in there? Look at the currents that I put down. What's the one thing I added to all the currents? Phase angle, right? Alpha. Alpha. So what I actually have to do here, all right, I have to include that phase angle. So that would be right here, because it would be I naught e to the j phase angle, and what I can do is just put it, I guess I can put it right here. And this would be I naught e to the j 2 alpha. And then dot, 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 and I'll get out of your way. It's going to be k I naught e to the j n alpha over r to the n. That's like, this should be minus right there. It's a minus. I'll clean it up for you in a second. And this is going to be times e to the minus j beta, and it's an r naught minus n d cosine of phi. And that's the progression. With me? Looks daunting, doesn't it? It isn't daunting. You're going to see this in a second. So just hold that together. And what I'm really going to do is say this. When I take a look at this, one thing I see, I'll make this argument, that 1 over R naught in magnitude is about equal to 1 over R1, is about equal to 1 over Rn. If you're a long ways away. Do you all agree with that? Right? And you all agree that we could take, and I'm going to do this, I could take and factor out the Ki naught now over just R naught. Do you agree with that? Out of each of these terms. Something else I can take out. Just look at this. Multiply this part through. I get an e to the minus j beta R naught there. I get an e to the minus j beta R naught there, don't I? As a matter of fact, I can factor that out. So I'm going to say, I'm just trying to do this to simplify stuff for you. I can say, in general, my total E field would be equal to K I naught over R naught, or any of these R's, all right? E to the minus J beta R naught. And then it's going to be 1 plus E to the J, and it's going to be beta D cosine of phi plus alpha plus E to the J beta D cosine of phi. I'm sorry. I did that wrong. It should be plus E to the J 2 times beta D cosine of phi plus alpha plus E to the, and then I'm going to do the dot, dot, dot. E to the J n beta D cosine of phi plus alpha. Can you all see that progression coming? Right? Because here I just have, when I take out E to the minus J beta R naught, I just have 1. E to the minus J beta R naught. Pull out front, I have E to the J, that's positive beta D cosine phi plus alpha. And you can progress all the way through. Do you all see this? It gets a little irritating. And now we make things, you can see this is reoccurring, right? Beta D cosine phi plus alpha, right? So we create a new symbol. This is the classic symbol. I call it a pitchfork, right? Capital Phi. And that right there is equal to beta D cosine of phi plus alpha. So now I can say my E total here is equal to K I naught over R naught E to the minus J beta R naught times 1 plus E to the J psi plus E to the J 2 psi plus E to the J 3 psi plus dot 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 E to the J n psi over 2. Y'all agree with that? Okay, actually I have n plus 1 and 10 is done. Because the first one I labeled as 0. With me, class?
Why are you dividing it by 2?
Oh, I'm sorry, not back there. Oh. E to the J n psi. I'm so sorry. I'm at the next step in my mind. I'm just thinking how much time. I'll stop and get this done. Now, this is sort of the definitive step, but I got to do one thing. You don't need to write this down, but you can if you want. I like doing this. So if you remember, in engineering, use a lot of these clever geometric sums. There's a lot of them. This one I like. If you had me for signals and systems, you know it probably. Whenever I have, when I take a look at this right here, I really have what? I have E to the J psi to the power n, don't I? Just look at that. That's n0, n1, 2, and so forth. You all see that? Right? N's just enough. That's what I have there. Well, this can be rendered as simply a to the n, right? Where n is just whatever I tip. You all with me? So here's the deal. When I want the summation from n equals, say, 0 to some n value of a to the n. That's really what I'm after, isn't it? I'm trying to sum up this series, correct, class? This is one of those things about engineers. These are things you'll learn to appreciate. I hope you love them. Well, what is this? That's really a to the 0 plus a to the 1 plus a to the 2 plus dot, dot, dot plus a to the n, right? You don't have to write this down, just watch. It's a good one. Anybody remember this? Yeah. If you had me for signals and systems, I think you remember. All right, now the next part is, well, what happens, and this is with mathematicians, they sit around and scratch their head about all the time. These type of problems. From 0 to n, but I multiply the whole thing by 1 minus a. Or better yet, I multiply it by a. Let's just do it this way. Well, if I multiply this by a, it's this series times a. Or it'll be a to the 1 plus a to the 2 plus a to the 3 plus dot, dot, dot plus a to the n plus 1. Take a look. You all agree? Because I put an a in front of it. Thanks for hanging in there. With me? All right. Well, what if I subtract this series from this series? What do I get? Well, I get 1 minus a, right? Times that series, don't I? Of a to the n from n equals 0 to n. But take a look. A to the 0 is 1, isn't it, class? So if I subtract them, I get 1. But notice, all these terms kill each other out. A1 kills out A1 upstairs, A2 upstairs, and so forth. Except for this last part, right? So it's 1 minus a to the n minus 1 is equal to that series times 1 minus a. Y'all see that? And therefore, if I divide both sides by 1 minus a, lo and behold, I have magically obtained the value of that series, regardless if there's an infinite number of terms or not. Agreed? I started at 0, by the way. Now, why am I doing that? Because now, I'll cut to the chase here. I'm almost out of time. Now, that whole series right there can be reduced to 1 minus plus 1, sorry, it should be a plus 1. 1 minus e to the j n plus 1 psi over 1 minus, in other words, this whole series, I'm going to get to this, is equal to k I naught e to the minus j beta r naught over r naught. Now this is an isotropic series. Then it's going to be times 1 minus e to the j, and this is going to be n plus 1 psi over 1 minus e to the j psi. Agreed? I'm not trying to scare you with this. I'm going to get to the chase, but you have to see the reasoning. Now, here's the deal. If I factor out an e to the j n plus 1 psi over 2 out of here, and an e to the j psi over 2 from here, I can do something really clever. guess why I did that? Here's why. What is e to the j alpha or j theta plus e to the minus j theta? It's what? 2j sine of theta, isn't it? Isn't this a sine over sine? Let me just cut to the chase. This whole thing reduces to this. Because I know I'm out of time. It's that. I want to make one comment. Wentworth's book, he does not do this. I do it because I think it adds an understanding to how you obtain circuits. That's how you get the electric field. Remember, in my case, I labeled N as, I started with 0 in my counting. So the actual number of antennas is going to be N antennas, or N plus 1 in mine. You follow me on that, class? In Whitworth's book, he's not going to use an N plus 1 and start with 0. This will be actually just N, where N's the number of antennas. And he'll have that, but he won't have this equation. That's the reason I wanted to show you this equation. Now this is for an isotropic radiator. I'm about out of time. Matter of fact, I am out of time. I don't want to hold you late. What I'm going to do is say that if I have the electric field for an isotropic radiator, if I multiply the electric field for any antenna that I know of, if all these antennas were half-wave dipole, I would multiply it by the electric field for a half-wave dipole. If all of them were short dipoles, I'd multiply it by the electric field from a short dipole. And if you take the isotropic radiation characteristics of an array and multiply it by the actual antenna that you're using, you get the total electric field. I'll put this stuff on one note. And if I wanted power, if I have the electric field, I square the electric field, right? And divide by 2/8 I can get the power density. I can get the normalized power. I'm going to give you the bottom line on this stuff. This is called a phased array antenna, and it's used for beam steering and magnification. You're going to see the gain goes up by n squared. Remember what I just said. So if you have a gain of 100, and you have 100 antennas, it would be 100 times 100 squared, or 10 to the 4th times 100. Do you understand that, class? 10 to the 4th is an incredible increase in gain. And this is used for extremely high gain antennas, what I'm showing. And the reason that alpha is there is for beam steering. I'm going to show you all this next time. Please come, I'm going to give you homework to get you set, okay? And I'm going to, I'm really trying to encourage you to do homework. Please do this homework. Y'all download or uploaded, I should say, the homework on campus.